Hello everybody, my name is Karthikeya Gupta and this is my video on Peterson's algorithm for mutual exclusion. Now, to go and discuss Peterson's solution for mutual exclusion, we must first understand that why it was devised, why it was developed. So the problem was a critical section problem. So to understand critical section problem, let us consider a system of n processes starting from P0 to Pn-1. Now, each process has a segment of code. It is called a critical section, in which the process may be accessing or updating data with at least one other processes. So, we have established that we must have a minimum of two processes, and each process has a segment of code that's called the critical section, and the rest of code comes under the remaining section. Now, the important feature of the system is that when one process is executing in its critical section, no other process is allowed to execute in its critical section. That is, no two processes are executing in their critical sections at the same time. So, for example, there are n processes, then only one of those n processes can execute in its critical state. Other n minus 1 processes will have to execute in their remainder section. That's not in the critical section. So, the critical section problem is to design a protocol that all the processes can use to synchronize their activity so as to cooperatively share data among themselves. So this was a problem, critical section problem, right? Now, the structure of any general process is this is the remainder section, this is the remainder section, and one part of it is the critical section. Now, each process must request permission to enter its critical section. The section of code implementing this request is the entry section. So this is the entry section. And here the process asks permission to enter into critical section. The critical section may be followed by an exit section, and the remaining code is the remainder section. So every other thing other than critical section comes under the remainder section. So this was the general structure of a process. Now, to discuss the Peterson solution, any solution that meets these three conditions is a Peterson solution. So the first condition is condition of mutual exclusion. We have discussed this before. If process P1 is executing in its critical section, then no other process can be executing in their critical sections. We have established that. Now, the progress. Now, which all other processes can take part, right? So if no process is executing in its critical section, that means no, not any of the n processes in its critical section, and some process wish to enter the critical sections. That means it makes a request. So only those processes that are not executing in their remainder sections can participate in deciding which process will enter in its critical section next. And this selection cannot be postponed indefinitely. Means you have to take this decision, and all those processes which are not executing in the remainder sections, they can participate in deciding. All those processes that are in their remainder sections, they cannot participate in their decision and hence cannot enter the critical state. Now, the third is bounded waiting. There exists a bound or a limit on a number of times other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. That means there are only limited opportunities other processes can go and execute their critical sections after any one of the processes has asked or requested to enter its critical section and that request is granted to the process. Now, after we have gone through the conditions, now let's come to the Peterson solution. Now, Peterson solution is restricted to two processes that alternate execution between their critical sections and remainder sections. For example, there are two processes, P0 and P1. Let's take them Pi and Pj for the simplicity. So, for example, if Pi is executing its critical section, then Pj will have to execute its remainder sections. And if Pj is executing its critical sections, then vice versa, Pi will have to execute its remainder section. So it is vice versa. One will execute its critical section and other will execute its remainder section. Now, Peterson solution requires two processes. We have established that to share, for example, that share two data items, uh, integer turn and boolean flag array 2. So now what's the solution, right? We have taken a look at all the three pre-requirements. Now, coming up to the solution. Here is a code given. We'll take a look at that. But first, let's understand what's written in here. Here is the critical section. This is the remainder section. There is a flag array, and there's a variable turn, and this is the while loop, and this is also the while loop. Now, the variable turn indicates whose turn is it to enter its critical section. So for example, if turn double equals to I, then process Pi is allowed to execute in its critical section. Here what we can see is turn double equals to J. That means this process J is allowed to execute its critical section. Now the flag array. Flag array is used to indicate if a process is ready to enter its critical section. For example, if flag of I is true, then Pi process is ready to enter its critical section. What we can see here is flag of I is equals to true. That means the process I is ready to enter its critical section, while the variable turn double equals to J means, or what it suggests is the process J is given the permission to execute its critical section. Now, after it executes its critical section, it comes out and start executing its remainder section, and this process, in the meantime, flag of I becomes false. Here it was true. It means it was ready to execute, and now it becomes false. That means it has been allowed to execute its critical section, while the process J executes its remainder section. So this is what the structure of a process in Peter's solution look like, where Peterson's solution for mutual exclusion states that when one process, for example J, is executing in its critical section, the other process I will have to execute its remainder section. And when this process J finishes its execution of the critical section, it comes out and starts executing its remainder section. Then, at that same time, the other process I will start its execution of critical section. So this is how the two processes communicate and execute their critical sections, vice versa. So this was it from my side. Thank you.